All right, greetings, welcome. So here's our last set of notes on Chapter 2, the PVT phase behavior of fluids. And in this set of notes, we're going to focus on cubic equations of state. So again, primarily in this course, when we're trying to quantitatively measure the PVT phase behavior of fluids, we'll work with steam tables. Well, we'll work with tabulated properties. Why? Because we're often working with water, so the steam tables are readily available in the back of the book. Or maybe we're working with a common refrigerant, such as refrigerant 134A, for which data is typically available. The other method that we'll typically use, right, when tabulated data says not available, is going to be our cubic equations of state. And so cubic equations of state are a robust method to quantitatively measure the PVT phase behavior of fluids, which are applicable to both liquids, vapor, and systems at vapor-liquid coexistence. Right, so that's going to take us well beyond what we just talked about in terms of corresponding states theory and Virial equation. Right, there's other equations of state that exist. Cubic equations are extremely common, especially in chemical engineering. They're indispensable when thinking about designing, say, a chemical plant or process. Okay? And why, should we be concerned about, cubic equations of state and being able to measure, say, data or measure systems for which data is not tabulated is, again, just think, I'm a design engineer. I'd say I'm a design engineer for Whirlpool, and I'm interested in finding a new refrigerant for a process. Maybe, someone in R&D has proposed 100 different candidates, right? And, I don't want to perform experiments and measure data for all 100 different possible candidates. It'd be great if I could predict, the phase behavior of those fluids and evaluate, which one might be a top contender, or, maybe not just predict, but maybe, measure some minimal amount of data and be able to use that in my assessment of the candidates. Okay, and so that's what we're going to get at with our cubic equations. And I will say that even when we have tabulated data, such as the steam tables in the back of the book, typically it's just tabulation of data computed using some accurate equation of state. Okay, so here we go. So, again, a refresher in terms of, where we've been and what we've been going, or where we're going, is we talked about corresponding states theory. So we talked about three-parameter corresponding states theory, in which we introduced the additional third parameter, the eccentric factor omega. Name typically associated with that is Lee Kessler. Okay, Lee Kessler just come in that we said, hey, it's Pitzer's the guy that kind of championed and developed these methods. Lee Kessler are the people that took these generalized graphs and tabulated them in a more convenient form to work with. Okay, but three-parameter corresponding states theory, or if you think about call them generalized correlations or Lee Kessler tables, they're typically limited to simple and normal or nonpolar molecules. Right, so the range of applicability, the type of system that they can measure is going to be limited. And typically, you're going to use these only to model gas phase systems. We then mentioned the Virial equation. So Virial equation, fundamentally is our only theoretically based equation of state. The challenge there is for most fluids, we typically only have, at most one or two Virial coefficients available. So if I just think of the truncated Virial equation, as in it's discussed in the text, in which I just have my second Virial coefficient, it really is just a first order correction to my ideal gas limit. Okay, and so the range of applicability of our truncated Virial is going to be extremely limited in applicability. And so here we're going to introduce our cubic equation of state, which is going to be applicable to modeling liquid phases and vapor phases and both simultaneously. Right, so we'll be able to model liquid phases, which take us beyond these corresponding states theory and Virial equation. As we'll present them here, the equations that we'll use here in this chapter will still, for the most part, be limited to more simple nonpolar molecules. So we're not really they really wouldn't necessarily be used in the present form or. So if you had no other data, you could use them to, say, model water. So, highly polar and associating systems. But in general, if you want to model something more complicated, you would use, an alternative equation of state. Okay, so cubic equations of state will be introduced here. They're going to be analytic methods which are capable of modeling liquids and vapors, so they're going to have a much broader range of applicability. Okay. So, two things I want to mention on equations of state is one, the equations of state that we'll talk about in this book or in this course are going to be van der Waals, SRK, and PR. Right? So Suave-Redlich-Kwong and Peng-Robinson. Van der Waals comes into play for historical purposes. It's the first cubic equation of state. You should never use it for any real calculation. We introduce it because all of our modern day cubic equations of state are just improvements or iterations upon van der Waals. SRK and Peng-Robinson, right? They are not the best equations of state. They are not the only equations of state out there. Okay, but we use SRK, we use Peng-Robinson because if you can use SRK, right, and primarily the book uses SRK. If you can do calculations with SRK, you can do calculations with any cubic equations of state. Right, so whatever you can do, if you're capable of working with SRK and solving problems with SRK, you can solve problems with anything. Okay, but as I mentioned in the last slide, right, the cubic equations of state that we'll mention, really are still limited in the systems that they can model. Right, is SRK going to be highly accurate for water? Well, it could probably do a decent job, but depending on what you're interested in, you might need something a little more accurate. Okay, and that's fine. Other equations of state exist which have been optimized for such systems. But again, if you can do calculations with SRK, you can do calculations with anything, right? And that's the reason for the introduction of SRK and Peng-Robinson is they're common, they're popular, they do a very good job, and if you could use those, you could use anything. And so kind of on that same note, the one thing I want to mention is I remember being an undergraduate student taking thermodynamics 1 and then later on thermodynamics 2. And we talk about equations of state, and later for chemical engineers, thermodynamics 2, we talk about excess Gibbs free energy models. And it's always overwhelming. How do I choose the right model, right? Hey, even in this course where we talk about van der Waals, again, never use van der Waals, but we introduce SRK and Peng-Robinson, how would I choose one over the other? How do I know which one to use? And, the answer to that is, experience, right? Quite literally. And so a book that's often recommended, that I would recommend to you, and the textbook even recommends, is there's a book called The Properties of Gases and Liquid by Poling, Prozis, and O'Connell. And in chapter 4 is devoted to equations of state for pure fluids. And so what they literally do is they take all available cubic equations of state available in the literature, and they use them to, predict or to calculate pure component properties for a wide range of fluids. And then they compare that predicted data or that calculated data using the model to reference data, and they use that to come up with some sort of assessment or recommendation of if you're trying to model, a alkane, this equation of state is going to work best. Right? So, I guess what I'm trying to say is, how do you choose an appropriate model? Well, that all comes from experience. All right. So I want you to be aware of, in this course, I want you to be aware of the tools available. Here, I want you to be comfortable working with the equation of state or understanding it. But do know that depending on, if you're that design engineer for Whirlpool and you're trying to model refrigerants, the first thing I would do is I would look in, say, a reference book like that for a suggestion in terms of which equation of state would be best for the system. For example, Peng-Robinson, which will come up, was optimized for applications in the petroleum industry by Robinson, who is a professor at the University of Alberta. Okay. So, experience, I always, like to tell students in class, that's why you get paid more the longer you're at a company, right? Because you have modeled similar systems, say for your company for X amount of years. So you kind of, develop this knowledge of best practices of how to solve problems. Okay. All right. So again, we're just trying to give an historical overview. And again, how would you choose in a cubic equation state in your future? Ask, senior person at your company for a recommendation. Have a look at Poling, Prozis, and O'Connell. where they would have tested, hundreds of different cubic equations of state for hundreds of different systems and have come up with recommendations, right? And that includes, complicated systems like water, acetic acid, right? So you name it, all right, they've tested it. Okay. So cubic equations of state aren't bad for those systems, but yeah. All right. And again, if you can work with one, you can work with them all. We just moved beyond van der Waals because van der Waals shouldn't be used for any sort of engineering calculation. All right, so now the idea of van der Waals equation of state. So van der Waals equation of state was developed by, you guessed it, Johannes van der Waals as part of his PhD thesis, and I recall the year was 1873. Okay. So again, think pre-computer age. So kind of the idea that I like to think about with the van der Waals equation of state is, what is an ideal gas? Well, an ideal gas is a system in which molecules don't interact and they don't take up space. And in, the ideal gas state, my equation of state, or the equation of state that I can derive from first principles, is PV equals RT. So for an ideal gas, P is equal to RT over V. All right. So now when we start to talk about the van der Waals equation of state and our cubic equation of state, we like to think of them as semi-theoretical based methods. Okay, call them semi-theoretical, and and essentially the idea is you have some sort of physical insight in terms of what's going on in your system. So you introduce some sort of physical insight, and then tweak your model based on that physical insight. Okay, so it's semi-theoretical. It's not something like the Virial equation, which you can derive from first principles. I'm going to start with something like the ideal gas equation of state. I'm going to bring in some insight in terms of how I believe molecules, are behaving in my system, and use that to modify my equation. Okay. And so I have my ideal gas equation of state, and then the thought exercise is, well, in an ideal gas, molecules don't interact and they don't take up space. So what van der Waals attempts to do is, correct for both of these assumptions. Okay, and so how we can think about these two terms is, so the common form of my Virial or van der Waals equation is P is equal to RT divided by V minus B minus A over V squared. Okay, so the first thing is, if I ignore this term in this box in blue here, if I just have P is equal to RT over V minus B. So if I compare that to my ideal gas equation of state, essentially what we've done is, in the ideal gas equation of state, you assume that the entire volume of your system is accessible to your molecules. Okay. Well, van der Waals says, well, that's not the case, right? Molecules occupy space, right? So another molecule can occupy, so let's say I have molecules 1 and 2, right, in my system. Molecule 2 can occupy the volume occupied by molecule 1. So the volume available to it is less than the total volume of my system. And so that's essentially what we try and account for here. So B is typically called the van der Waals volume of my system, of my molecule. So it tries to account for, so V is my molar volume, the volume per mole. B accounts for the physical space occupied by the molecules in our system, right, here on a molar basis. So V minus B then accounts for the the free volume, right, available to the molecules in our system. Okay. Again, we call this a semi-theoretical model, right? So the idea is molecules occupy space, total volume is not available, right? And so trying to modify, say, our ideal gas equation of state to account for this. Okay. The second term that gets added on here, right, is this minus A over V squared. Okay, so the idea behind this is that, okay, so now we've accounted for the fact that molecules occupy space, but molecules are also going to interact. Okay, and at this point it had been shown, I believe it was by London, right? So the idea of London dispersion interactions. So from quantum mechanics, so for two helium atoms, it could show by perturbation theory that the interaction energy is going to scale as 1 over r to the 6. And so what's added here is this term that scales as 1 over volume squared. Why 1 over volume squared? Well, volume scales as interaction distance cubed, right? R cubed. 1 over V squared is going to scale as 1 over r to the 6, right? And our dispersion interactions are going to scale as 1 over r to the 6. So van der Waals adds this term to account for the fact that molecules occupy space. All right, and then it adds this term to try and account for the fact that molecules interact. Okay. Again, we call it semi-theoretical in that there's some physical intuition, right, or some theory, right, in the case of that attractive term for the form of these terms, where these come from. But it's not something that's derived from first principles, some theoretically correct equation, right? We're trying to develop some quantitative equation which we can use to make improved predictions as compared to ideal gas equation of state. So you account for the fact that molecules take up space and the fact that molecules interact. So this term negative a over v squared, that's the term that accounts for attractive interactions. And this red term here is going to account for the fact that molecules occupy space. Okay, so we have two parameters, right? So now we have this additional parameter a, which is an attractive term, and b, an excluded volume term. Okay, so you have a model now with two parameters. Okay, all right, so it gets the correct limiting behavior. All right, so in this case, v goes to infinity, z goes to 1. Okay, so now a couple of things. All right, so first is, why do we call these cubic equations of state? So as he proposed the equation, P is equal to RT over V minus B minus A over V squared. We call that a pressure explicit equation. All right, so the idea being, if I know my two parameters A and B, if I were to specify, say, T and V, I could use that to calculate P. Okay, so that's great, but typically the problem's more so if I specify, say, P and T, and I want to calculate V. Okay, you can't directly solve this equation for V. And as we mentioned earlier, all right, V has some issues, right? And so it's often more convenient to work with Z, right? Why Z? Right? In general, Z is going to be bound between 0 and 1, okay? In addition to being dimensionless. So it's going to be a dimensionless quantity with the values typically between 0 and 1, where the range of V is going to be much larger. And so what works out is if you were to take the van der Waals equation of state and solve it for Z, what you end up with, all right, and so, again, the range of z's are typically between 0 and 1. In the supercritical region, you can get values between or above 1. Okay, but in general, for problems of typical interest, right, we're dealing with z's between 0 and 1. Okay, so if you were to go back to the van der Waals equation of state and essentially put it in a form, or substitute in the definition of compressibility, and then solve for z. Okay, what you end up with is an equation which is cubic in z. Okay, where here we've just introduced some additional parameters a prime and b prime, which are just functions of TP, and then parameters a and b. Okay, so when you plug in the definition of compressibility and solve for z, you end up with an equation that's cubic in z. Okay, so it's cubic in z. That's where you get cubic equation of state. We work with z for convenience. Cool. Okay, so our cubic equation state is cubic, right, in z. And so what that tells us is that we can have up to 3 real roots. Okay, and so typically what happens, so one, you can have up to 3 real roots. And so the real significance of that is I can simultaneously model both my vapor and liquid phase. So if I have a system at vapor-liquid coexistence, I can simultaneously model both the liquid and vapor at coexistence, right? Cool. So I can model a system at vapor-liquid coexistence. Now you can get up to 3 real roots, right? And so generally what happens is if you are near saturation, right, then you'll get 3 real roots, right? The liquid, the root closest to 0, the smallest root would correspond to my liquid, the largest root would correspond to vapor, the one in the middle I would throw out, okay? And what do I use, liquid or vapor? Well, if I'm at coexistence, I use both. Otherwise, I would need to have an idea I would need to know what phase I'm in terms of determining if I'm in that liquid region, so compressed or subcooled liquid, or vapor, superheated vapor. Okay, so I would need to know what phase I'm in terms of determining which one I use. But you never use the middle one. And then, typically if you're away from your coexistence curve, so I think about, P versus V phase diagram. So if I'm away from that dome in my compressed liquid region, right? Once you get away from the phase diagram or from that saturation curve, typically you'll just get one real root. Okay. So again, if you get three real roots, you always throw out the middle one. If you're at coexistence, then you've got your liquid and vapor. Life is good. Otherwise, you need to know what phase you're in, what region you're in terms of determining which root you keep. Okay. But it's cubic, so you can simultaneously model both your liquid and vapor, so you can get both at once. Okay, so it's a cubic equation, right? So something else that turns out to be nice in terms of working with z, right, in this cubic equation is that there's a lot of numerical and mathematical techniques out there for solving for the roots of a cubic equation. So I'll provide two tutorials. I'll often use MATLAB just because it's easy, but you could just as well use Excel. So in Excel, you could come up with a guess of the value of z, and then use goal seek to solve for these z for which this equation is satisfied. And if you're looking for a liquid root, right, you can start with a z close to some small z. If you do have a vapor, you can start with some large z closer to 1. And use that to try and solve for said root. All right. Now, you do have this parameter a and b in the van der Waals equation of state. Okay, but where van der Waals went from this is quite clever. So again, when we talked about looked at a p versus v phase diagram, right, we pointed out that if you look at the critical isotherm, right, the critical isotherm is special in that the first derivative is 0 at the critical point. Okay. First derivative 0, and the second derivative is also 0. It goes through an inflection point. It goes from being concave up to concave down. And so van der Waals, notice this for all fluids. Okay, my critical isotherm, the first and second derivative are 0 at the critical point. And the beauty of that is I have two parameters, a and b. Well, if I know that the first and second derivative of my critical isotherm is 0 at the critical point, that gives me two constraints. So using two constraints, I could solve for my two parameters. Okay, and we won't go through all the math. Okay, but van der Waals did this, right? He went through this exercise. Okay, and what he ended up finding is that he could relate little a and little b to my critical properties. Okay, so he finds that little a is equal to this 9 RTC VC over 8, and b is equal to VC over 3. So we can relate A and B to critical properties, right? So he uses the properties of that critical isotherm to give two constraints to solve for A and B. Okay, so it's cool, right? So essentially uses corresponding states theory, if you will, to solve for. I'm not sure I understand. Is there something else I can help with? To solve for parameters A and B. I didn't get that. Could you try again? Okay, so that's cool, and then. But it is limited. So using two parameter corresponding states theory, he predicted the critical compressibility is always 3/8, and so that's not universally true, right? So it does have some limitations. Okay, but that's van der Waals. That's the first one. Okay. And then where we go from there is, so again, van der Waals you can think of as a two parameter corresponding states theory. Okay, is okay that van der Waals equation state works okay, but what posits do, right, to try and tie it back into corresponding states theories, we would add a third parameter. So the two other cubic equations of state which come in this course is, or in this text, is a Soave-Redlich-Kwong equation of state. And essentially what they did is, remember, van der Waals is P is RT divided by V minus B minus A over V squared. And so what he does is he modifies this second term. Right? So if I expand it out, instead of v times v plus b, it's v squared plus bv. So in this attractive term, he modifies the denominator by adding a plus bv. Okay, so you can go through the same exercise in terms of getting an equation which is cubic in z. But then, right, what's done is you introduce, we force essentially our equation of state not just to obey our properties at our critical isotherm, or that the first and second derivative are 0 at the critical point, but we also impose this constraint of the eccentric factor, right? So we know the eccentric factor is related to the reduced saturation pressure and reduced temperature of 0.7, right? So we can use that to enforce another constraint, if you will. All right, and so here you have it. suave over the Kong equation of state. All right, so he empirically adjusts the attractive term. All right, so his assumption is a limitation of the van der Waals equation of state is in how it's modeling attractive interactions, tweaks it, and then also adds another constraint that the equation must obey, the eccentric factor. Goes through the same exercise, and you could come up with, so again, equation that's cubic in Z, and then you could come up with relationships for the parameters in your model. Okay, so that's cool. So the book seems to primarily use SRK. Again, if you can use SRK, you can use them all. The last one the book mentions, though, is Peng-Robinson equation of state. And so again, compared to van der Waals, he's just modifying the attractive term, and then he's also adding this additional constraint of the eccentric factor. Okay, you can go through the same exercise. You get an equation that's cubic in Z. All right, here's my same parameter A prime and B prime, but then you can solve for all of your model parameters in terms of your critical point, so critical properties, and eccentric factor. Okay, so cool. All right, Peng-Robinson. All right, I'm more familiar with maybe as a chemical engineer, in that Robinson was a faculty at University of Alberta, and so his equation was engineered for petroleum applications. So the petroleum industry came to him and said, so this is when Calgary was really big in oil industry. We need an accurate equation of state for reservoir modeling, and so his equation was optimized for petroleum applications. Okay, but that's the idea. Many others exist. Right, most equations of state are just iterations on the original van der Waals equation of state. Okay, what makes them different, right, is they're often engineered or designed for specific applications. So Peng-Robinson was optimized for petroleum industry applications, right? So typically they're just, optimized for a particular application. How do you choose? Again, it's experience, or you go and you look up in a handbook for a given type of system. There's, you can find a recommendation of what type of equation of state to use. Hope that helps. Next, we'll get on to solving some problems.